So in this section, we're going to talk about the fundamental identities in trigonometry. Before we go into that, let's just take a moment to understand what an identity does for us and maybe what an identity is. An identity is any equation that is true for all values of the variables. In other words, I could choose any number out there for x and y, and if I plug it into the left-hand side and then to the right-hand side, it makes both sides equal. So any number out there, any number I randomly choose for both x and y, as long as I replace them on the left-hand side and the right-hand side, causes this statement to be true. That's what an identity does for us. Now that's different from an equation. Okay, so in an equation we're used to solving for a particular variable. In other words, there's only one number out there in the entire world that says when I multiply that number times 3, I get 12. Okay, so an equation gives us a single value, whereas an identity is something that I can pick an infinite number of values for. Now, an identity allows us to rearrange and maybe simplify some sort of algebraic expression. Okay, because I know it's a true statement, I can just replace one for the other. So for example, if I had this expression here that said something squared plus something else squared plus 2 times these letters, if I recognized that this thing that I'm working on is really just a rearrangement of my identity, then I can simply replace it with what the identity is, and I can rewrite it as p plus z quantity squared. Now, I might want to do that if I'm trying to solve an equation. We do it a lot in trigonometry whenever we are solving trig equations. We might do it in calculus when I want to replace something to simplify it. So that's what an identity does for us. Now back to our notes. We've talked up until this point about several identities. We know that we have the reciprocal identities given by these three right here. I have the quotient identities, which can look like this, and we've done the Pythagorean identities, which are given by these three statements here. Understand that when I have an identity, I can also rewrite an identity to serve the purpose I need. So for example, if I'm looking at the Pythagorean identity that says sine squared theta plus cosine squared theta is equal to 1, and maybe I want to solve this, or I want to rearrange that identity so sine squared theta is on the outside, then I would just subtract cosine to the right hand side, and I have created an identity or that I can use for a different purpose. Okay, I'm still going to use the identity, but maybe I just need it in a different form, in other words. Now, the last set of identities that are on here are dealing with negative angle identities. And because you're going to ultimately need to memorize this list of identities that are growing here, and I suggest maybe writing these identities down, keeping track of them on a note card as you move through these sections. But let's try to think about the negative angle identities for a second and help with your memorizing of them. I'm going to focus on these middle two right here, which deal with both cosine and secant, and we know that those two are related. These are the only two that are different from the remaining 4 identities, so I want to focus on them first. When I am finding the cosine of a negative angle, that's going to be equal to just the cosine of the positive angle. So the cosine of a negative theta is equal to just cosine theta. In other words, they're the same. Same thing with secant negative theta is just the same as secant positive theta. That's different from the remaining 4 over here. If I take the sine of negative theta, then the answer is going to be a -1 times the sine of positive theta. Okay, so these remaining 4 out here are kind of opposite of what you think. And these 2 on the inside follow the same pattern where the cosine of negative theta is the same thing as the cosine of positive theta. Okay, now let's try to use these identities in an example. In this first example, we're looking at, I want to find each of the function values that you'll see throughout this example. and I want to be able to find those function values using only the identities that we've been discussing. So if cosine theta is equal to 5/8 and I know that theta is in quadrant 4, I want to know what is sine theta. Using an identity, I approach this by thinking to myself, well, is there an identity that has cosine in it and leads me to sine? You know, it somehow relates these two right here. Hopefully already you're thinking to yourself, sine squared theta plus cosine squared theta equals 1, which is the Pythagorean identity, has cosine and sine in it, and maybe I want to try that one. Now this is the identity that I do want to use because I already know what cosine is, I know what 1 is, and that only leaves one piece of this puzzle that I now have to solve for. So let's go ahead and substitute in sine squared theta plus 5/8 squared is equal to 1. Solving for sine squared theta, I'm going to square this fraction and subtract it from 1 using my calculator. So sine squared theta is equal to 39 over 64. Since I'm solving for just sine theta, I'm going to take the square root of both sides. And when I do that, I find that sine theta is the square root of 39 over the square root of 64, which is 8. Now before I leave this answer, since I'm taking the square root, I want to check. I know that theta was in quadrant 4, so sine needs to be negative in quadrant 4. Alright, let's look at the next example here, or the next piece of this example. Now I want to find out what tangent theta is. Again, only using the identities that we know so far. So is there anything that relates tangent to sine and possibly cosine? And there is. The quotient identity says tan theta is sine over cosine. I know both sine and cosine, so I can simply replace this and solve for tangent. So this is our quotient identity. When I replace sine theta with what I just calculated it to be as negative square root of 39 over 8 divided by cosine theta, which is 5/8, now all I need to do is simplify this. So when we divide fractions, we're actually multiplying the reciprocal. So this is negative square root of 39 over 8 times the reciprocal, which is 8/5. You can see that these 8's are going to cancel out, leaving me with negative square root of 39 over 5. So I also want to ask myself, in quadrant 4, is tangent negative? And yes, it is. Okay, and the last one deals with the secant of negative theta. This is going to introduce us to the negative angle identity. But before I get there, maybe I want to change this into something that I recognize first. I know that secant theta is equal to 1 over cosine theta from the reciprocal identities. So we're going to rewrite this as 1 divided by what cosine theta is, which is 5/8. So 1 divided by 5/8 is the same thing as multiplying by the reciprocal, which is 8/5. Now the negative angle identity says if I have the secant of a negative theta, that's the same thing as the secant of positive theta. So therefore the sign of this doesn't change, because I know that secant theta, I know that theta is positive in quadrant 4, and so that's how come the sign doesn't change on this. So the answer would be 8/5.